Cosmic voids, the loneliest places in the universe. Imagine, if you will, a place so empty that you could travel for hundreds of millions of light years without encountering a single galaxy. A region of space so vast and so vacant that our entire observable universe, with its trillions of galaxies, its countless stars, its infinite wonders, would seem crowded by comparison. A darkness so complete that if you could somehow stand within it, the night sky would contain not the familiar tapestry of stars we see from Earth, but almost nothing at all. Just a handful of distant, impossibly faint lights scattered across an otherwise empty cosmos. These places exist. They're called cosmic voids, and they represent something that challenges our deepest intuitions about the universe. We tend to think of space as being filled with things: stars, planets, galaxies, nebulae, all the luminous matter that makes the universe beautiful and fascinating. But the truth is stranger and more unsettling. Most of the universe is empty. Not just empty, but profoundly, almost incomprehensibly empty. And within this general emptiness, there are regions that are emptier still. Vast bubbles of near nothingness that dwarf anything we can easily imagine. Before we journey deeper into this mystery, I'd like to invite you to join our community of cosmic explorers. If you find yourself captivated by these questions about the universe's structure and the strange territories that exist within it, please consider subscribing to this channel. Now, let us descend into the void. The discovery of cosmic emptiness. The story of cosmic voids begins, as many astronomical discoveries do, with patient observers noticing something that didn't quite fit the expected pattern. In the 1970s and early 1980s, astronomers began creating three-dimensional maps of galaxy distributions. This was painstaking work, measuring the distances to thousands of galaxies, plotting their positions, trying to understand how matter was distributed across vast stretches of cosmic space. What emerged from this work was shocking. Galaxies weren't scattered randomly throughout space, as many had assumed. Instead, they were arranged in an intricate pattern, clustered together in some regions, stretched into long filaments in others, and completely absent from vast territories. The universe, it turned out, has a structure, and that structure looks remarkably like a sponge, or perhaps like soap bubbles, with galaxies concentrated on the surfaces and edges, while enormous empty regions fill the interiors. The first major void to be recognized was discovered in 1981 by Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman. They were surveying a region of space in the constellation Bootes when they noticed something peculiar. A spherical region roughly 330 million light-years in diameter that contained almost no galaxies at all. Where they expected to find hundreds or thousands of galaxies, they found fewer than a dozen. This discovery was initially met with skepticism. Surely there must be galaxies there that simply hadn't been detected yet. Perhaps the apparent void was just an observational artifact, a trick of incomplete data. But as surveys became more comprehensive and technology improved, the void remained. It was real, and it wasn't alone. As astronomers mapped larger and larger volumes of space, they discovered that voids aren't rare cosmic accidents. They're fundamental features of the universe's large-scale structure. The cosmos is permeated with these immense empty regions, separated from each other by walls and filaments of galaxies. Universe, at its largest scales, is mostly void. The architecture of emptiness. To truly appreciate cosmic voids, we need to understand the scale we're discussing. Human minds evolved to comprehend the distances we might walk in a day, or perhaps the voyage we might sail across an ocean. We can stretch our intuition to grasp the distance to the moon, or even to the outer reaches of our solar system. But cosmic voids exist on scales that utterly overwhelm human intuition. A typical cosmic void might span 200 million light-years in diameter. Some are significantly larger. The largest known void, discovered in 2007 and known as the Giant Void or the Eridanus supervoid, stretches approximately 1 billion light-years across. To put this in perspective, Light, traveling at 186,000 miles per second, would need 1 billion years to cross this region. Our entire Milky Way galaxy is about 100,000 light-years in diameter. You could fit 10,000 Milky Way galaxies across the width of a large cosmic void with room to spare. The local group, the gravitationally bound collection of galaxies that includes the Milky Way, Andromeda, and about 50 smaller galaxies, spans roughly 10 million light-years. You could fit 100 local groups across a large void. But size alone doesn't capture what makes voids so strange. It's the emptiness that truly defies comprehension. Within a typical void, the density of matter might be only 10% of the average density of the universe. Some voids are even emptier, containing perhaps only 1% or 2% of the average cosmic density. What does this mean practically? It means that if you were somehow positioned in the center of a large cosmic void, and if your eyes could detect distant galaxies, which they can't, we need powerful telescopes for that, your night sky would contain almost nothing. Where we on Earth see thousands of stars visible to the naked eye, and where our telescopes reveal billions of galaxies, you would see perhaps a handful of extremely faint, distant galaxies scattered across the entire celestial sphere. The universe would appear almost completely dark. Take a moment to sit with that image. Not darkness like a moonless night on Earth, where stars still fill the sky. Not darkness like the space between stars in our galaxy, where other stars and nebulae still surround you. But a darkness so profound that looking in almost any direction reveals nothing. Just empty space stretching toward an impossibly distant horizon. If this exploration is resonating with you, if you're feeling that particular combination of wonder and existential vertigo that comes from contemplating the truly vast, I encourage you to like this video. It helps others discover these cosmic mysteries, and it lets me know that this slow, contemplative approach to astronomical wonder is valuable to you. The cosmic web, voids in context. To understand voids, we must first understand the structure they're part of, the cosmic web. This is perhaps the most beautiful, large-scale pattern in nature, and it tells us something profound about how the universe evolved. Imagine, if you will, the universe shortly after the Big Bang. Matter was distributed almost uniformly throughout space. Not perfectly uniform, but close. Quantum fluctuations had created tiny variations in density, regions that were slightly more dense and regions that were slightly less dense. These variations were minuscule, perhaps 1 part in 100,000. But gravity is patient and inexorable. Regions that were slightly more dense had slightly more gravitational pull. They attracted more matter, becoming denser still. This increased density meant stronger gravity, which attracted even more matter. Meanwhile, regions that started slightly less dense lost matter to their denser neighbors, becoming even less dense in comparison. Over billions of years, this process, called gravitational instability, amplified those tiny initial variations into the cosmic web we see today. Matter collapsed along certain lines, forming filaments. Where filaments intersected, matter accumulated in great clusters and superclusters of galaxies. And the regions from which matter was drawn became increasingly empty, the cosmic voids. The result is a structure of breathtaking intricacy. If you could step back and view the distribution of galaxies across billions of light-years, you would see a pattern that looks remarkably organic. Long, delicate filaments of galaxies connect dense nodes where galaxy clusters reside. Stretched between these filaments are vast, roughly spherical voids, the empty spaces, the territories from which matter has been evacuated. This pattern isn't unique to our particular region of space. Wherever astronomers look, at whatever distance, they find the same basic structure. Galaxies arranged in webs and walls, surrounding and defining vast voids. The cosmic web is a fundamental property of our universe, a signature of how gravity has sculpted matter over cosmic time. But here's what's truly remarkable. Simulations of the universe's evolution, based purely on our understanding of physics and gravity, reproduce this structure with extraordinary accuracy. Starting from simple initial conditions, a nearly uniform distribution of matter with tiny random variations, computer simulations watched over by astrophysicists generate cosmic webs that look nearly identical to what we observe in the real universe. The voids emerge naturally from the mathematics of gravity acting over cosmic time. This tells us something profound. The emptiness isn't arbitrary or accidental. It's a necessary consequence of how matter behaves under gravity in an expanding universe. The voids are as fundamental to cosmic structure as the galaxies themselves. You can't have one without the other. The universe has organized itself into regions of concentration and regions of absence, and both are essential parts of the pattern. What lives in the void? When we say cosmic voids are empty, we must be precise about what we mean. They're not empty in the absolute sense. They're not perfect vacuums devoid of everything. Rather, they're profoundly underdense compared to the rest of the universe. So what, if anything, exists within these immense territories? First, there are a few galaxies. Not many, perhaps 1/10 the number you'd expect in a typical region of space, but they're not entirely absent. These void galaxies are fascinating objects in their own right. They tend to be smaller than average, bluer than average, indicating active star formation, and often spiral rather than elliptical in shape. Why would void galaxies be different? The answer likely relates to their environment. Galaxies in dense regions, in clusters and along filaments, interact frequently with their neighbors. They experience gravitational encounters, they collide and merge. They're subjected to processes that strip away their gas and quench their star formation. These environmental effects tend to produce large, reddish, elliptical galaxies, the galactic equivalent of retirement communities, where star formation has largely ceased. Void galaxies, by contrast, live in isolation. They rarely encounter neighbors. They retain their gas reserves. They continue forming stars at a leisurely pace. They evolve quietly and independently, following their own internal rhythms rather than being shaped by violent external interactions. In some sense, they're the universe's hermits, solitary, independent, developing according to their own nature. Between these rare void galaxies lies the intergalactic medium, gas so diffuse that it's almost undetectable, but not quite absent. This gas, mostly hydrogen and helium, exists at extremely low density. Where the intergalactic medium in denser regions might contain 1 atom per cubic centimeter, the gas in voids might contain 1 atom per 10 cubic centimeters, or even less. This rarefied gas is significant for several reasons. First, it's gradually falling toward the void boundaries, being gravitationally attracted toward the denser regions where galaxies congregate. This slow cosmic migration of matter from voids to filaments has been occurring for billions of years and continues today. The voids are, in a sense, being emptied further over time, becoming progressively less dense as what little matter they contain is drawn away. Second, this gas carries information about the universe's history. By studying its properties, its temperature, its ionization state, the elements it contains, astronomers can learn about past epochs when the universe was younger and quite different. The void gas is, in some sense, primitive material that has been less processed and recycled than gas in denser regions. It offers a window into cosmic history. And then there's dark matter. Dark matter, that mysterious substance that makes up roughly 85% of all matter in the universe, but remains invisible and undetected except through its gravitational effects. Dark matter doesn't emit, absorb, or reflect light. It interacts with normal matter only through gravity. And it's everywhere, including in cosmic voids. Even in the emptiest voids, dark matter is present, though at reduced density compared to the rest of the universe. Simulations suggest that dark matter in voids isn't uniformly distributed, but forms its own delicate substructure, tendrils and sheets of dark matter stretching across the void interior, invisible scaffolding in the darkness. This dark matter, though we cannot see it directly, shapes the evolution of voids. Its gravity, weak though it is in these underdense regions, still influences how the void expands and how matter at the void boundaries behaves. The visible structure of the cosmic web, the galaxies we can observe, is really just a tracer of the underlying dark matter distribution. The true architecture of the universe, including the voids, is written in dark matter. If you're finding these layers of mystery fascinating, the visible emptiness, the invisible dark matter, the isolated galaxies living their quiet lives in cosmic isolation, please take a moment to subscribe to this channel. There are so many more cosmic mysteries to explore together, and your subscription helps this community grow. The physics of void expansion. Here's something particularly strange about cosmic voids. They're expanding faster than the universe as a whole. This isn't a violation of physics. It's a natural consequence of how matter and gravity interact. But it produces an eerie effect. The voids are growing. The emptiness is spreading. To understand this, we need to consider two competing forces that govern the universe's large-scale behavior: the overall cosmic expansion and local gravitational attraction. The universe as a whole is expanding, a consequence of the Big Bang and the continued momentum of that primordial explosion. This expansion means that distant objects are receding from each other, not because they're moving through space, but because space itself is stretching. This expansion affects everything, everywhere, at all scales, though its effects are only noticeable across very large distances. But gravity works against expansion. Where matter is dense, gravity is strong, and it pulls matter together, counteracting the cosmic expansion. In regions like galaxy clusters, gravity has overwhelmed expansion entirely. These regions have collapsed, and the galaxies within them are gravitationally bound, orbiting each other rather than receding. In cosmic voids, however, matter is scarce, which means gravity is weak. There's not enough gravitational attraction to significantly resist the cosmic expansion. So voids expand faster than the universe's average expansion rate. They're growing, ballooning outward, pushing the surrounding walls of galaxies further apart. This creates a kind of feedback effect. As voids expand, push matter toward the filaments and clusters at their boundaries. This makes the filaments denser, which increases their gravitational pull, which draws even more matter from the voids, which makes the voids emptier still. The rich get richer, and the empty get emptier. Over cosmic time, this process leads to an increasingly structured universe. The contrast between voids and filaments becomes more pronounced. The voids grow larger and emptier, while the filaments become denser and more pronounced. The universe's large-scale pattern becomes ever more defined, like a developing photograph gradually revealing its image. But here's where it becomes truly strange. There's also dark energy to consider. Dark energy is an even more mysterious substance than dark matter, a property of space itself that causes cosmic expansion to accelerate. Dark energy seems to provide a kind of anti-gravity, pushing everything apart. In dense regions where gravity is strong, dark energy's effects are negligible compared to gravitational attraction. But in cosmic voids, where gravity is weak, dark energy dominates. This means that voids are expanding even faster than we'd expect from normal cosmic expansion alone. They're being actively pushed outward by dark energy's repulsive effect. The result is that voids are among the most dark energy-dominated regions in the entire universe. They're territories where this mysterious cosmic force plays a disproportionately large role in determining structure and evolution. By studying voids carefully, measuring their sizes, their expansion rates, their shapes, astronomers hope to learn more about dark energy's properties and how it influences cosmic evolution. The sound of creation, voids, and the cosmic microwave background. There's a strange and beautiful connection between cosmic voids and the earliest moments of the universe. To understand it, we need to travel back in time, back to when the universe was only 380,000 years old. At that early epoch, the universe was filled with hot, dense plasma, a soup of electrons and protons so hot that atoms couldn't form. Light couldn't travel freely through this plasma. It was constantly being absorbed and re-emitted, scattered in random directions. The universe was opaque. But as the universe expanded, it cooled. Eventually, it cooled enough for electrons and protons to combine into neutral hydrogen atoms. This moment, called recombination, had a profound effect. Suddenly, light could travel freely. Photons that had been trapped in the plasma were released, streaming through space in all directions. Those photons have been traveling ever since, and we can detect them today as the cosmic microwave background radiation, the oldest light in the universe, the afterglow of the Big Bang. This light carries information. Tiny variations in its temperature, differences of only a few parts per million, reveal where matter was slightly denser or slightly less dense when the light was released. These variations are the seeds from which all cosmic structure grew. The denser regions would eventually become galaxy clusters and filaments. The less dense regions would become voids. But there's more to the story. Before recombination, when the universe was still plasma, sound waves were propagating through it. These were true acoustic waves, pressure waves traveling through the hot plasma at about half the speed of light. They were generated by the same density fluctuations that would eventually create cosmic structure. These sound waves left an imprint. They created a characteristic scale, a preferred distance, at which matter became slightly more clustered. This scale, about 450 million light-years in today's expanded universe, is called the Baryon Acoustic Oscillation, BAO scale. It's like a cosmic ruler, a standard distance imprinted in the universe's structure, and cosmic voids reflect this scale. When astronomers measure the typical separation between voids, they find it corresponds closely to the BAO scale. The voids remember, in a sense, the sound waves that propagated through the infant universe. Their sizes and spacing preserve information about conditions when the universe was less than 400,000 years old, billions of years before the first stars even formed. This connection between voids and the cosmic microwave background is profound. It means that by studying voids today, we're not just learning about current cosmic structure, we're seeing echoes of creation itself, patterns imprinted in the first moments of cosmic history and preserved in the distribution of emptiness. Life in a void, a thought experiment. Let's engage in a thought experiment, one that might help us truly appreciate what cosmic voids represent. Imagine that our galaxy, the Milky Way, wasn't located where it is, on the edge of the local group, which itself lies along a filament in the cosmic web. Instead, imagine the Milky Way existed within a large cosmic void. You're still on Earth. Your planet is unchanged. Your solar system is the same. Your galaxy remains structurally identical. But now, you're located in one of those profoundly underdense regions, far from any galaxy clusters, far from any dense filaments. You're in the deep emptiness. What would be different? First, and most dramatically, your night sky. When you look up, you see far fewer stars than we actually do. The Milky Way still arches overhead. Our galaxy's own stars are still visible. But beyond that, things become strange. When you turn your telescopes toward the sky, searching for other galaxies, you find almost nothing. We, in the real universe, can observe millions of galaxies with modern telescopes. We photograph deep space fields showing thousands of galaxies in a region of sky no larger than a grain of sand held at arm's length. But in a void, those observations would reveal mostly darkness. Perhaps a handful of small, faint galaxies would be visible, scattered at immense distances. But the universe would appear largely empty, largely dark. Your astronomy would develop quite differently. The realization that other galaxies exist, a discovery that revolutionized our understanding in the 1920s, might come much later, if at all. With so few nearby galaxies to observe, you might conclude that the Milky Way is essentially the entire universe, surrounded by an infinite void. Cosmology, the study of the universe's structure and evolution, would be vastly more difficult. Many of the observations that have shaped our current understanding depend on having many galaxies to observe, compare, and analyze. In a void, with only a few isolated examples, progress would be slower and more uncertain. Your understanding of cosmic structure would be distorted. You might know intellectually that matter exists in other places. Those few distant galaxies prove as much. But you wouldn't grasp the true structure of the cosmic web. You wouldn't realize that you live in an anomalous region, that most matter in the universe is arranged in filaments and clusters, not scattered in isolation. You'd be cosmologically provincial without knowing it. There's something poignant about this scenario. Intelligence arising in a void would face profound observational handicaps. The universe would hide its true nature, presenting a misleadingly empty face. Void dwellers might take longer to understand their cosmic context, or might develop theories about why the universe is so empty when in fact they simply live in an atypical region. This thought experiment isn't just whimsical. It connects to deep questions about observation and understanding. How much does our cosmic address influence what we can know? Are there aspects of reality that are hidden from us simply because of where we happen to be located? Could there be civilizations elsewhere in the universe whose cosmic view is radically different from ours because they're situated in different types of regions? And there's a deeper question still. Might we ourselves be missing something? We don't live in a void. We're in a relatively typical location along a filament in the cosmic web. But could there be other aspects of cosmic structure, other scales of organization that we're failing to detect because of the limitations of our particular observational situation? I'm curious about your intuitions here. If you had to choose, would you rather live in a universe with a rich, visible cosmic web full of galaxies, or in a void where you experience more isolation, but perhaps more local uniqueness? Share your thoughts in the comments. I find these questions endlessly fascinating, and I learn from every perspective offered. The mystery of void dynamics. Despite decades of study, cosmic voids still harbor mysteries that astronomers are actively working to understand. One of the most intriguing involves the detailed physics of how voids affect nearby galaxies. We know that galaxies at the edges of voids are being pushed and pulled by complex gravitational forces. The void interior has weak gravity trying to pull them inward, while the filaments beyond the void have strong gravity trying to pull them outward. The void itself is expanding, which tends to push the boundary galaxies away. These competing effects create intricate dynamics. Observations suggest that galaxies at void boundaries have unusual properties. They often show signs of recent star formation, as if something about the void environment triggers new bursts of stellar birth. They're frequently aligned in peculiar ways, with their rotation axes oriented preferentially in certain directions relative to the void. And they show velocity patterns that suggest coherent motion. They're not just randomly distributed, but seem to be participating in large-scale flows. What's causing these effects? The full answer isn't yet clear. It likely involves a combination of factors. The stretching of space as the void expands, the gravitational pull from filaments, the infall of gas from the void interior, and perhaps subtle effects from dark matter and dark energy. Disentangling these different influences requires sophisticated observations and careful modeling. Another mystery involves the void interiors themselves. Are they truly as empty as they appear, or might there be populations of objects we're simply failing to detect? Could there be numerous faint, low-mass galaxies within voids that escape detection because they're too dim for current telescopes? Or dark galaxies, hypothetical objects composed mostly of dark matter with very little visible matter, that would be nearly invisible but gravitationally significant. Some observations hint that void interiors might not be completely smooth and empty, but could contain subtle substructure, smaller, secondary voids within larger voids, or perhaps tendrils of slightly enhanced density crisscrossing the emptiness. If confirmed, this would suggest that cosmic structure is more intricate than currently understood, with hierarchies of organization extending into even the emptiest regions. There's also the question of void evolution over cosmic time. We can observe voids at different distances and therefore at different epochs in cosmic history. By comparing voids from different eras, astronomers can study how emptiness evolves. Do voids maintain their sizes, or are they growing over time? Do they merge with each other, creating ever larger empty regions? How do their properties change as the universe ages and dark energy becomes increasingly dominant? Initial studies suggest that voids do grow over time, as expected from theory, but the details are complex and still being worked out. Understanding void evolution is important because it constrains cosmological models. Different theories about dark matter, dark energy, and cosmic expansion predict different patterns of void growth. Voids and the nature of dark energy. Let's linger on dark energy for a moment, because cosmic voids might hold crucial clues to understanding this most mysterious component of the universe. Dark energy is profoundly strange. It seems to be a property of empty space itself, a baseline energy density associated with the vacuum. Unlike matter, which becomes less dense as the universe expands, the same amount of matter spread over a larger volume, dark energy maintains constant density. As the universe grows, the total amount of dark energy increases to maintain the same energy per unit volume. This leads to dark energy's characteristic effect, causing cosmic expansion to accelerate. The more space there is, the more dark energy there is, which drives even more expansion, creating even more space and thus even more dark energy. It's a runaway process that appears to be driving the universe toward an increasingly rapid expansion. But here's what's mysterious. We don't really know what dark energy is. The simplest explanation is that it's Einstein's cosmological constant, a property of space-time itself. But it could be something more exotic, a new field pervading space, or a modification to gravity at cosmic scales, or something even stranger that we haven't imagined yet. Cosmic voids provide a unique laboratory for studying dark energy, because they're regions where dark energy's effects should be particularly pronounced. In these underdense territories, gravity is weak, so dark energy's repulsive effect dominates. By carefully measuring how voids expand, how their shapes evolve, and how they affect surrounding matter, astronomers can constrain dark energy's properties. Different models of dark energy make slightly different predictions about void behavior. If dark energy's strength changes over time, a possibility that some theories allow, that would affect void expansion rates in measurable ways. If dark energy interacts with matter or dark matter, most models assume it doesn't, but it's worth checking. That might create subtle effects in void environments where dark energy is dominant. The stakes are high because dark energy determines the universe's ultimate fate. If dark energy maintains its current strength, the universe will expand forever, eventually cooling to near absolute zero as galaxies recede beyond each other's cosmic horizons. If dark energy strengthens over time, it could eventually overcome not just cosmic expansion, but even local gravitational binding, a scenario called the Big Rip, where everything, including atoms, is torn apart by runaway expansion. If dark energy weakens or reverses, the universe might eventually stop expanding and collapse back on itself in a big crunch. Cosmic voids, in their profound emptiness, might help us discern which future awaits. The emptiness, it turns out, speaks volumes. The void galaxy enigma. Let's return to those lonely galaxies within voids, the scattered island universes that somehow exist in the cosmic wilderness. These objects present puzzles of their own. First, there's the question of how they got there. If voids have been emptying over time, with matter being gravitationally drawn toward the denser filaments and clusters, why are there any galaxies left in void interiors? You might expect them to have migrated out by now, or never to have formed there in the first place. The answer seems to involve the initial conditions of cosmic structure. Not every region that would become a void started absolutely empty. Some contained slight overdensities, places where matter was marginally more concentrated. These small overdensities could collapse under their own gravity to form galaxies, even as the surrounding material migrated away toward denser regions. So void galaxies are, in some sense, relics. They're survivors that managed to condense before the void emptied around them. They formed in place and then watched as their neighborhood was evacuated, leaving them in increasing isolation. But void galaxies aren't just interesting for their location. They're scientifically valuable because they represent a different pathway of galaxy evolution. Most galaxies we study live in rich environments where interactions are common. They merge with neighbors. They have their gas stripped away by hot intergalactic plasma. They're subjected to tidal forces from nearby massive objects. All these environmental effects profoundly shape how galaxies evolve. Void galaxies experience none of this. They evolve in isolation, affected mainly by their own internal processes. By studying them, astronomers can learn what galaxy evolution looks like when environmental effects are minimized. It's like having a control group in a cosmic experiment. Most galaxies develop under environmental pressure, but void galaxies show us the alternative. And what we find is fascinating. Void galaxies tend to be smaller than average, suggesting they haven't grown through mergers. Bluer than average, indicating ongoing star formation rather than quenched aging populations. Gas-rich, since there's nothing to strip away their star-forming fuel. Spiral or irregular in shape, rather than the elliptical shapes common in dense environments. Rotating in ways that suggest they haven't experienced significant gravitational interactions. In essence, void galaxies are simpler, more pristine, still actively forming stars and evolving according to their own internal rhythms. They offer windows into how galaxies behave when left to their own devices, and they help astronomers disentangle internal evolution from environmental effects. There's also something emotionally resonant about void galaxies, at least to this observer. They're cosmic hermits, island universes separated by hundreds of millions of light-years from their nearest neighbors. If there's intelligence in a void galaxy, beings looking up at their night sky, they'd see a profoundly lonely cosmos. Their nearest galactic neighbor might be visible only as a faint smudge in powerful telescopes, impossibly distant, utterly unreachable. Yet they endure. They form stars, they evolve, they persist in the darkness. There's a kind of quiet dignity in that persistence. Supervoids and the cold spot. Among cosmic voids, some stand out for their extraordinary size or strange properties. These supervoids push the boundaries of what we thought possible in terms of cosmic emptiness. The largest known void, sometimes called the giant void or Eridanus supervoid, spans approximately 1 billion light-years. To call it vast is such an understatement as to be almost meaningless. This is a region where the fabric of space stretches across unimaginable distances, mostly empty, occasionally interrupted by lonely islands of matter, but predominated by absence. What makes this particular supervoid especially intriguing is its possible connection to one of cosmology's persistent mysteries: the cold spot in the cosmic microwave background. Cosmic microwave background, as mentioned earlier, is remarkably uniform. Temperature variations are typically only a few parts per million. But there's one region, a roughly circular patch about 5 degrees across in the southern sky, where the microwave background is significantly colder than average, about 70 microkelvins colder than expected. This cold spot has puzzled cosmologists since its discovery. Why would this particular region be notably colder? Various explanations have been proposed, ranging from mere statistical flukes to exotic physics involving parallel universes colliding with ours. But one intriguing possibility involves the supervoid. The idea is based on something called the integrated Sachs-Wolf effect. As photons from the cosmic microwave background travel through the universe, they pass through regions of varying gravitational potential. When photons enter a gravitational well, a denser region, they gain energy. When they climb out, they lose energy. Normally, these effects cancel. The energy gained entering equals the energy lost exiting. But in an expanding universe dominated by dark energy, things are different. As photons travel through a void, the void is expanding. By the time photons climb out of the void's gravitational potential, the void has grown. It's a shallower well than when the photons entered. The result is that photons lose more energy climbing out than they gained falling in. They're redshifted, which we observe as cooling. A sufficiently large void along our line of sight could, in principle, create a measurable cold spot in the cosmic microwave background. The Eridanus supervoid is positioned appropriately to potentially explain the observed cold spot. If this explanation is correct, we're seeing a void's gravitational imprint on the universe's oldest light, an enormous empty region leaving its signature on photons that have been traveling for 13.8 billion years. However, the story isn't settled. Some analyses suggest the supervoid isn't quite large enough or dense enough to fully explain the cold spot's magnitude. Other nearby voids might contribute. Or the cold spot might have multiple causes, with the supervoid playing a partial role. Or it might be a coincidence, with the supervoid and the cold spot being unrelated phenomena that happen to lie in the same direction. The mystery endures, and supervoids remain subjects of intense study. Each new survey that maps larger volumes of space discovers additional supervoids, revealing that these extreme examples of cosmic emptiness are less rare than once thought. The universe, it seems, is quite capable of creating regions of extraordinary absence. If this journey into emptiness is captivating you, if you're feeling that peculiar mix of wonder and existential contemplation that these cosmic scales evoke, please take a moment to like this video and share it with others who might appreciate this slow exploration of the universe's structure. And I'm genuinely curious, do you find cosmic voids beautiful, unsettling, both, or something else entirely? The comment section is a space for sharing these reflections. The future of void research. Astronomy is entering a golden age of void studies. New telescopes and surveys are mapping the universe in unprecedented detail, revealing voids across vast swaths of cosmic space and time. These observations are transforming our understanding. The Dark Energy Spectroscopic Instrument, DESI, for instance, is currently conducting the most ambitious redshift survey ever attempted, measuring the distances to tens of millions of galaxies. This will create three-dimensional maps of cosmic structure spanning billions of light-years, revealing thousands of voids in exquisite detail. By analyzing these voids statistically, their sizes, shapes, expansion rates, and evolution, astronomers hope to constrain dark energy's properties with unprecedented precision. The Vera C. Rubin Observatory, when it comes fully online, will repeatedly photograph the entire southern sky, creating a time-lapse view of the universe. This will enable studies of how voids evolve and how galaxies at void boundaries move and change over time. The sheer volume of data will allow statistical studies that were previously impossible. Future space telescopes, like the Nancy Grace Roman Space Telescope, will have the resolution and sensitivity to study individual void galaxies in detail, even at large distances. This will reveal how void galaxy properties change over cosmic history, and how they compare to galaxies in denser environments at different epochs. But perhaps most exciting are the theoretical advances. Increasingly sophisticated computer simulations can now model the universe's evolution in remarkable detail, following dark matter, gas, stars, and galaxies across billions of years. These simulations are revealing the intricate physics of void formation and evolution, the subtle effects of dark energy, and the complex interplay between voids and the cosmic web. By comparing simulations with observations, astronomers can test theoretical models and refine their understanding. When simulations accurately reproduce observed void properties, it validates the underlying physics. When discrepancies appear, they point toward new physics or missing ingredients in the models. One particularly intriguing direction involves machine learning and artificial intelligence. These tools are being applied to void identification and characterization, finding patterns in cosmic structure that human analysts might miss. They're also helping optimize observation strategies, determining which voids to study in detail to maximize scientific return. The ultimate goal is a comprehensive understanding of cosmic voids as part of the larger cosmic web. How do voids form? How do they evolve? How do they affect nearby structures? What can they tell us about dark matter and dark energy? How do they fit into the universe's life story? We're closer to answering these questions than ever before, yet each answer raises new mysteries. The voids, in their emptiness, remain endlessly fascinating. Philosophical implications of cosmic voids. There's something philosophically provocative about cosmic voids. They challenge our intuitions about existence, structure, and meaning in ways that matter even beyond astronomy. Consider the basic question: what is a void? Is it truly a thing, or is it merely the absence of things? In one sense, a void is defined purely by what it lacks. It's a region where galaxies, matter, and density are deficient. It has no existence independent of that lack. Yet, in another sense, voids are as real as galaxies. They have shapes, sizes, boundaries. They evolve over time. They affect neighboring structures. They're identifiable, measurable, and consequential. They're features of the universe as genuine as any cluster of galaxies. This mirrors ancient philosophical debates about whether absence can be considered a form of existence. Can nothing be something? Is emptiness a type of presence? Cosmic voids don't resolve these debates, but they give them physical instantiation. They're territories where absence becomes substantial, where nothing becomes a defining characteristic. There's also something humbling about voids. We often think of the universe as full of galaxies, stars, planets, perhaps life. We think of space as a canvas filled with wonders, a grand theater of cosmic drama. And while this isn't wrong, it's incomplete. Most of the universe, by volume, is void. Emptiness predominates. The galaxies and stars that captivate us are, in cosmic terms, rare exceptions, isolated islands in an ocean of absence. This shifts perspective. Perhaps the universe's default state is emptiness, and matter is the anomaly. Perhaps the stars and galaxies are brief, localized fluctuations in an otherwise vacant cosmos. From this viewpoint, existence itself, the presence of matter, energy, structure, and complexity, is the improbable condition that requires explanation. And yet, here we are. We exist not in a void, but in a galaxy, in a star system, on a planet, in one of those rare, improbable locations where matter has concentrated, where structure has formed, where complexity has emerged. We're the exceptions, inhabitants of an atypical region, living in circumstances that most of the universe doesn't share. Does this make our existence more precious or more contingent? Are we lucky to inhabit a matter-rich region, or does it simply reflect a selection effect, that observers like us can only arise where conditions permit complexity, which means we necessarily find ourselves in atypical locations? These questions don't have definitive answers, but they shift how we think about our cosmic situation. Cosmic voids serve as a reminder that the universe we observe from Earth is not representative. The view from here is privileged, biased toward structure and matter, because that's where we can exist. The universe as a whole is emptier, lonelier, and stranger than our local experience suggests. The aesthetic of absence. There's a particular aesthetic quality to cosmic voids that's worth contemplating. In human culture, we often find beauty in presence, in elaboration, detail, complexity, richness. Art that fills space, music that fills silence, architecture that fills landscapes. We're drawn to abundance, to fullness, to the intricate and the ornate. But there's another aesthetic tradition that finds beauty in absence, in simplicity, in emptiness. Japanese ma, the concept of negative space, the pregnant pause in music. minimalist art that uses absence as its primary medium, the vastness of empty deserts or oceans. These traditions recognize that emptiness has its own power, its own emotional resonance. Cosmic voids embody this aesthetic of absence at the grandest scale imaginable. They're the ultimate negative. Space, the cosmic equivalent of silence between notes. They define and emphasize the structures that surround them. Filaments and clusters become more striking, more significant, more beautiful when we recognize they're bordered by vast regions of absence. In a sense, the voids make the cosmic web possible. Without emptiness, there can be no pattern. Without absence, there can be no structure. The galaxies matter partly because they're not everywhere. They're specific locations, they're gathering into filaments and clusters, their avoidance of voids. These patterns are only meaningful against a backdrop of emptiness. This suggests a different way of looking at voids, not as failures of the universe to produce structure, but as essential components of cosmic architecture. They're not gaps or flaws, but deliberate notes in the composition, long-held silences that give meaning to the sounds that surround them. If you find yourself moved by this contemplation, I invite you to subscribe to this channel. There are infinite layers to cosmic mystery, and this community is devoted to exploring them with patience, wonder, and thoughtful attention. Cosmic loneliness and connection. The title of this exploration mentions loneliness, and it's worth examining that characterization. Are cosmic voids truly lonely? Loneliness is, of course, a human emotion, inappropriate to attribute to regions of space. And yet the metaphor feels apt. Loneliness isn't just about physical isolation, it's about the absence of connection, the gulf between self and other. It's about being surrounded by distance so great that interaction becomes impossible. It's about inhabiting a space where signals sent out receive no response, where presence goes unwitnessed, where existence unfolds in isolation. In this sense, cosmic voids are profoundly lonely places. A galaxy within a void is isolated by distances so vast that communication with neighboring galaxies would be essentially impossible. Even if such galaxies harbored civilizations, they would be cosmically alone, unable to reach or be reached by others, living out their existence in isolation. Light itself enforces this loneliness. Even traveling at the universe's speed limit, photons would need hundreds of millions of years to cross a void. There's no practical way to send messages, share information, or establish connection across such distances. The inhabitants of one void galaxy, if they exist, are cut off from the inhabitants of other void galaxies in a way that's absolute and permanent. This cosmic loneliness mirrors a deeper truth about existence. We're all, in various ways, isolated. Consciousness is inherently solitary. Each mind is a universe unto itself, directly accessible only to itself. We can communicate, share experiences, form connections, but there's an irreducible separateness to being a distinct entity. The void galaxy's isolation is just an extreme version of the isolation that characterizes all existence. And yet, and this is the beautiful paradox, we're also deeply connected. Every atom in your body was forged in stars. The calcium in your bones, the iron in your blood, the oxygen you breathe. All these elements were created in stellar furnaces and scattered across space by dying stars. You're literally made of stardust, composed of matter that has journeyed across space and time to temporarily assemble into the form reading these words. More than that, you're connected to the voids themselves. The emptiness shaped the cosmic web, which determined where matter concentrated, which influenced where stars formed, which governed which elements were created, which ultimately allowed planets and life and consciousness to emerge. The voids, in their absence, are part of your cosmic genealogy. So while voids represent isolation, they also represent connection, not in spite of their emptiness, but because of it. The structure of the universe, including both the dense regions and the empty ones, is a single interconnected pattern. The voids and the galaxies are two aspects of one cosmic whole, each meaningless without the other. Living in an accelerating universe. As we conclude this exploration, it's worth considering what cosmic voids might reveal about the universe's ultimate fate. Current observations suggest that dark energy, which dominates void dynamics, is causing the universe's expansion to accelerate. This acceleration has profound implications. If it continues, the universe will grow at an ever-increasing rate. Structures that are currently gravitationally bound, galaxy clusters, galaxies, even solar systems, will remain intact. But everything beyond these bound structures will recede beyond cosmic horizons. Eventually, billions of years from now, galaxies outside our local group will become unreachable, having receded so far that their light can no longer reach us. The observable universe will shrink, not because anything is moving toward us, but because accelerating expansion creates a limit to how far light can travel. In this future, cosmic voids will grow ever larger and emptier. The contrast between voids and filaments will become more extreme. Eventually, even the filaments themselves will begin to fragment as cosmic expansion overwhelms progressively smaller scales of gravitational binding. The ultimate result, trillions of years hence, is a cold, dark, and profoundly empty universe. Individual galaxies or galaxy groups will become islands of structure in an otherwise empty cosmos. Isolated, alone, unable to interact with any other structures because everything else has receded beyond reach. In a sense, everywhere will become a void. The current voids are previews of the universe's ultimate condition. This seems melancholic. The universe, currently still structured and connected, evolving toward fragmentation and isolation. But perhaps there's another way to view it. The current epoch, the age we inhabit, is special. It's a time when structure exists, when galaxies fill the sky, when the cosmic web is visible and magnificent. It's a narrow window in cosmic history between the initial smooth simplicity after the Big Bang and the eventual empty simplicity of the far future. We're living in the universe's brief, anomalous period of complexity and structure. Cosmic voids remind us of this. They show us what emptiness looks like, what the universe becomes when matter is scarce and dark energy dominant. And by contrast, they highlight how remarkable our local environment is, how unlikely, how temporary, how precious. Every star you see, every galaxy photographed by telescopes, every intricate structure in the cosmic web, these are transient phenomena, present for only a fraction of the universe's total lifespan. We're witnesses to a particular era, a special moment when the universe is interesting, structured, and connected. The voids, in their emptiness, underscore the rarity and value of what exists in non-void regions. They're reminders to pay attention, to appreciate, to recognize that we inhabit an extraordinary time in cosmic history. The wonder of cosmic voids. So we return to where we began, cosmic voids, the loneliest places in the universe. Vast regions where galaxies are scarce, where matter has been evacuated, where emptiness predominates. Territories so immense that our grandest structures, galaxies, clusters, superclusters, seem tiny by comparison. Places where darkness and silence reign, where the usual cosmic bustle gives way to profound absence. We've explored how they form, how they evolve, what they contain, what they reveal about dark matter and dark energy, and the universe's fundamental structure. We've contemplated their philosophical implications, their aesthetic qualities, their future evolution. We've imagined what it might be like to inhabit one, and we've recognized how they shape the universe we actually inhabit. But perhaps the deepest insight is this. Cosmic voids teach us that existence is defined as much by absence as by presence. The universe's structure emerges from the interplay between density and emptiness, between matter and void. You cannot have one without the other. The galaxies are meaningful because they're not everywhere. The cosmic web is beautiful because it's surrounded by emptiness. In the end, cosmic voids invite us to expand our definition of what counts as interesting, what deserves attention, what contributes to understanding. They challenge us to find significance in absence, structure in emptiness, beauty in silence. They're reminders that the universe is larger, stranger, and more varied than our immediate experience suggests. That beyond the familiar richness of galaxies and stars lie vast territories of a completely different character. And they pose an enduring question. In a universe where most of space is void, where emptiness predominates, where isolation is more common than connection, in such a universe, what does it mean that we exist here, in this rare pocket of matter and structure, briefly witnessing cosmic complexity before it disperses into the approaching emptiness? I don't have a definitive answer to that question, but I find the asking valuable, and I find the voids themselves endlessly fascinating in their profound, mathematical, absolute emptiness. Thank you for joining this exploration into cosmic absence. If these mysteries resonate with you, please share this video with others who might appreciate this contemplative approach to the universe's wonders. And I invite you to share your own reflections in the comments. What emotions do cosmic voids evoke in you? Do you find them terrifying, beautiful, thought-provoking, or something else entirely? Your perspectives enrich these explorations, and I'm genuinely eager to hear them. Until our next journey into cosmic mystery, keep looking up, even toward the empty spaces. To truly appreciate cosmic voids, we should understand how astronomers actually find and map these immense empty regions. It's a remarkable detective story involving some of humanity's most sophisticated instruments and cleverest techniques. The challenge is immediate and profound. How do you detect something defined by its absence? You can't photograph a void the way you photograph a galaxy. There's nothing there to emit light, nothing to capture with a telescope. Instead, astronomers must map what surrounds the voids, the galaxies, and infer the empty regions from their distribution. This requires redshift surveys, one of astronomy's most labor-intensive undertakings. The process works like this. You point a telescope at a region of sky and identify every visible galaxy. Then, for each galaxy, you measure its redshift, the stretching of its light caused by cosmic expansion. This redshift tells you how far away the galaxy is. By combining position on the sky with distance, you create a three-dimensional map showing where galaxies actually are in space. It sounds straightforward, but the reality is monumentally demanding. Modern redshift surveys measure distances to millions of galaxies. Each measurement requires capturing a galaxy's spectrum, spreading its light into component wavelengths, and identifying specific spectral features that reveal the redshift. This takes telescope time, computational resources, and years of painstaking work. The Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken, spent over a decade mapping the three-dimensional distribution of galaxies across large swaths of the sky. The data revealed the cosmic web in stunning detail: filaments, clusters, walls, and voids arranged in intricate patterns. Subsequent surveys like the 2DF Galaxy Redshift Survey and the ongoing Dark Energy Spectroscopic Instrument Project have pushed even deeper and wider, mapping ever larger volumes of space. But even with millions of galaxies mapped, identifying voids isn't trivial. The boundary between a void and a filament isn't sharp. Density gradually decreases as you move from filaments toward void interiors. Different algorithms define voids differently, using various mathematical criteria to decide where a void begins and ends. Some algorithms look for spherical regions of underdensity. Others identify voids as watershed basins in the cosmic density field, regions that would drain toward local density minima if matter could flow freely. Still others use sophisticated topological methods, identifying voids as connected regions below some density threshold. Each method has strengths and weaknesses, and they don't always agree on exact void boundaries. This might seem like a problem, but it actually reflects something deep. Voids aren't discrete objects with clear edges. They're features of a continuous density field, and how you define them depends on what questions you're trying to answer. Modern void-finding algorithms run on supercomputers, processing terabytes of survey data to identify thousands of voids across vast cosmic volumes. The catalogs they produce, lists of void positions, sizes, shapes, and properties, are scientific treasures, enabling statistical studies that reveal how voids fit into cosmic structure. There's something profound about this entire enterprise. We've developed the technology to map emptiness billions of light-years away. We've created mathematical frameworks for characterizing absence. We've turned nothing into data, and from that data, we're learning about the universe's fundamental nature. It's a very human accomplishment, taking the unobservable and making it observable, the intangible and making it measurable. The Boötes Void, Portrait of Emptiness. Among all known cosmic voids, one holds special historical significance: the Boötes Void, the first supervoid ever recognized. Its discovery story is worth telling in detail because it captures the surprise and wonder that comes from finding something so unexpected. In 1981, astronomers Robert Kirshner, Augustus Oemler Jr., Paul Schechter, and Stephen Schechtman were conducting a redshift survey of galaxies in the constellation Boötes. They expected to find galaxies distributed more or less uniformly across the survey region, perhaps with some clustering, but nothing too dramatic. Instead, they found something shocking: a roughly spherical region about 330 million light-years in diameter, containing almost no galaxies at all. Where statistical expectations suggested they should find approximately 2,000 galaxies, they found only about 60. The space was essentially empty. Their initial reaction was skepticism. Survey data always has gaps and incompleteness. Perhaps this apparent void was just a region where their observations had missed galaxies for technical reasons? They checked and rechecked their data, looking for errors or biases that might explain the emptiness. But the void remained. As word of discovery spread, other astronomers began calling it the Great Void, or simply the Boötes Void. Some jokingly referred to it as the Great Nothing. The discovery made headlines. Here was a region of space so empty that if our Milky Way were located at its center, humanity wouldn't have discovered other galaxies until the 1960s, when telescopes became powerful enough to detect the void's sparse, distant galaxy population. Subsequent observations have refined our understanding of the Boötes Void. It's not completely empty. It contains about 60 known galaxies, though this is still only about 10% of the expected number. These galaxies are predominantly small, blue, actively star-forming systems, the characteristic population of void galaxies. The void isn't perfectly spherical either. Like most voids, it's somewhat elliptical, stretched along certain axes. This elongation reflects the cosmic web's influence. Voids tend to be squeezed by the surrounding filaments and clusters, creating slightly flattened or elongated shapes. One of the Boötes Void's most intriguing features is a chain of galaxies running through its interior, a kind of tenuous filament crossing the emptiness. This suggests that even void interiors aren't perfectly homogeneous, but contain subtle substructure, hints of organization within the emptiness. The void's discovery transformed cosmology. Before 1981, theorists had predicted that voids should exist based on gravitational instability theory. But finding such a massive example confirmed those predictions dramatically. It proved that cosmic structure operates on scales far larger than individual galaxies or galaxy clusters. The universe has architecture at scales of hundreds of millions of light-years, and voids are fundamental components of that architecture. Today, the Boötes Void remains intensely studied. It's close enough, relatively speaking, the nearest edge is about 700 million light-years away, to observe in detail, making it an ideal laboratory for void physics. Astronomers continue to discover new galaxies within it, study its expansion, and use it to test cosmological theories. There's something poetic about the Boötes Void being the first supervoid discovered. It's as if the universe revealed its capacity for profound emptiness in a single, unmistakable example, a demonstration that space can be organized not just by what's present, but by what's conspicuously absent. The local void, our cosmic neighborhood's empty quarter. While the Boötes void is impressive, there's another void that's even more relevant to humanity: the local void, a large, underdense region quite close to our own cosmic neighborhood. The local void sits adjacent to our local group of galaxies. It spans roughly 150 million light-years and contains significantly fewer galaxies than average cosmic density would predict. We're not inside it, we're near its edge, on the boundary between the void and a region of higher density, called the local sheet. This proximity makes the local void scientifically valuable. It's close enough to study individual galaxies within it, close enough to measure detailed motions and properties, close enough to use as a laboratory for understanding void physics without the observational challenges posed by more distant voids. But the local void's proximity also raises fascinating questions about cosmic geography and its effects. Does living near a void influence our cosmic observations in subtle ways? Does it affect the motions of nearby galaxies, including our own? The answer appears to be yes. Galaxies near void boundaries experience a peculiar gravitational effect. They're repelled by the void's underdensity, while simultaneously attracted to the denser regions beyond. This creates characteristic velocity patterns. Galaxies tend to flow away from void centers and toward surrounding filaments and clusters. Our local group is part of this flow. We're moving not just because of the attraction of distant massive structures like the Virgo supercluster, but partly because we're being pushed by the local void's expansion. The void is, in a small way, influencing our trajectory through space. More intriguingly, the local void may affect which galaxies we can easily observe. Because we're on the void's edge rather than deep within it, we have a somewhat richer view of cosmic structure than we would from the void's interior. But we're also not in the densest possible region. There are richer environments, galaxy clusters and supercluster cores, where observers would see even more dramatic cosmic structure. Our position is, in some sense, cosmologically suburban. We're in a moderately dense region, near but not within a void, close to but not within a major cluster. This might seem unremarkable, but it raises an intriguing question. Could our location influence which cosmological questions we find natural to ask? If we lived in a dense galaxy cluster, cosmic voids might seem more dramatic and puzzling. How can such enormous empty regions exist when our local experience is of density and crowding? If we lived in a void interior, the cosmic web itself might seem more mysterious. Why do galaxies gather into filaments when our local experience is of isolation and emptiness? Perhaps our intermediate position, able to see both voids and structure, neither overwhelmed by crowding nor isolated in emptiness, gives us a relatively unbiased perspective on cosmic architecture. Or perhaps it biases us in ways we don't recognize, making certain aspects of cosmic structure seem natural when they're actually the aspects visible from our particular location. These are subtle epistemological questions, but the local void makes them concrete. We can study this nearby underdense region in detail, compare it to more distant voids, and ask whether proximity influences understanding. I'm curious about your intuition here. Do you think our position in the universe, near a void but not within it, near clusters but not within them, affects how we understand cosmology? Could observers in different locations develop notably different pictures of cosmic structure? Share your thoughts in the comments. These questions fascinate me, and I genuinely value diverse perspectives on them. Voids across cosmic time, evolution, and history. One of the most revealing ways to study cosmic voids is to observe them at different distances and therefore at different epochs in cosmic history. Because light takes time to travel, when we observe distant objects, we're seeing them as they were in the past. By comparing voids at various distances, we can study how they evolve over cosmic time. The picture that emerges is fascinating. Voids in the early universe, observed at high redshift, seen as they were billions of years ago, are less pronounced than voids today. The contrast between voids and filaments was weaker in the past. The cosmic web existed, but was less sharply defined, less structured, more subtle. This matches theoretical expectations perfectly. Shortly after the Big Bang, matter was distributed nearly uniformly. Tiny initial density variations, quantum fluctuations inflated to cosmic scales, were the seeds of structure, but they were minuscule. Over billions of years, gravitational instability amplified these variations. Dense regions attracted more matter and became denser still. Underdense regions lost matter to their denser neighbors and became emptier still. The process is progressive and cumulative. The contrast between high-density and low-density regions grows with time. In the early universe, voids were merely slightly less dense regions. As the universe aged, they became progressively emptier as matter drained toward filaments. Today, voids are starkly underdense. In the future, they'll be emptier still. We can observe this evolution directly by mapping voids at different redshifts. High redshift voids, seen as they were several billion years ago, are smaller and less empty than nearby voids seen as they are today. The void population evolves. Voids grow, empty out, and possibly merge with neighboring voids. This evolution tells us something crucial. Cosmic structure is not static. The universe we see today is a snapshot in an ongoing process. The cosmic web was less pronounced in the past and will be more pronounced in the future. Voids are part of this dynamic evolution, expanding and emptying as dark energy and cosmic expansion overcome the weak gravity within underdense regions. But there's a complication: dark energy. About 5 billion years ago, the universe transitioned from being matter-dominated, where gravity was the main force shaping cosmic structure, to dark energy-dominated, where dark energy's repulsive effect became increasingly important. This transition affected void evolution. Before dark energy dominated, voids were still growing primarily through gravitational effects, matter draining from underdense regions toward denser ones. After dark energy became dominant, void expansion accelerated. Dark energy pushes against gravity everywhere, but its effects are most pronounced in underdense regions where gravity is weak. This means that void evolution has accelerated in recent cosmic history. Voids today are growing faster than they would have in a universe without dark energy. Future voids will grow faster still as dark energy becomes increasingly dominant. By studying void evolution across cosmic time, measuring how their sizes, shapes, and emptiness change, astronomers can constrain dark energy's properties. Different models of dark energy predict different evolution patterns. Observations of voids thus become tests of fundamental physics, turning emptiness into a cosmological laboratory. There's something conceptually beautiful about this. The universe's emptiest regions, the places where matter is most scarce and structure least apparent, are revealing some of the universe's most fundamental properties. Absence becomes informative. Nothing tells us about everything. The mathematics of voids, topology and geometry behind the visual beauty of cosmic voids lies elegant mathematics. Understanding voids rigorously requires sophisticated geometric and topological tools that reveal patterns invisible to casual observation. One key concept is topology, the mathematical study of shape and connectivity. Topologically, cosmic voids resemble bubbles or cells in a foam. They're simply connected regions. You can draw any loop within a void and continuously shrink it to a point that pack together, sharing boundaries with neighboring voids and with the filaments that surround them. The cosmic web's topology is characterized by several important numbers. The genus of a structure describes how many handles it has, how many holes pass through it. The cosmic web, with its interconnected filaments and voids, has high genus. It's topologically complex, more like a sponge or Swiss cheese than a simple arrangement of separate objects. Mathematicians and cosmologists have developed measures to quantify this topology. The Euler characteristic, for instance, captures fundamental topological properties of the cosmic web. Minkowski functionals describe shape properties like volume, surface area, and curvature. These measures, when applied to observed galaxy distributions, reveal the cosmic web's mathematical structure. What's remarkable is how well simulations match observations. When cosmologists run computer simulations of structure formation, starting from simple initial conditions and following matter evolution under gravity and dark energy, the resulting topology matches observed cosmic structure with extraordinary precision. The simulated cosmic web has the same Euler characteristic, the same distribution of void sizes, the same Minkowski functionals as the real universe. This agreement is profound, evidence that we understand the physics governing cosmic structure formation. The match between simulation and observation isn't approximate or coincidental, it's detailed and specific. The mathematics of cosmic voids, it turns out, follows directly from fundamental physics. Geometrically, voids have interesting properties. They're approximately ellipsoidal, stretched and flattened by the gravitational influence of surrounding structure. The degree of ellipticity reveals information about the cosmic web's formation history and the strength of gravitational effects. Void shapes are characterized by 3 axis lengths, and their ratios reveal whether voids are spherical, all 3 axes equal, prolate ellipsoids, 1 axis longer, like a cigar, or oblate ellipsoids, 1 axis shorter, like a pancake. Statistical studies show that voids are typically somewhat oblate, flattened in one direction, reflecting the anisotropic gravitational forces that shape them. The distribution of void sizes follows specific mathematical patterns. There's a characteristic scale, related to the baryon acoustic oscillation scale, imprinted in the early universe, and voids cluster around this scale with predictable variations. 2 small regions don't qualify as voids. They're just random underdensities. And 2 large regions are rare. They require special initial conditions. This size distribution, like the topology, can be predicted from theory and matches observations beautifully. It's another case where mathematics derived from fundamental physics successfully describes cosmic structure's statistical properties. Geometers studying cosmic voids have also discovered fractal-like properties. At different scales, the cosmic web shows similar patterns: smaller voids within larger empty regions, subfilaments within main filaments, hierarchy and self-similarity. This fractal character isn't perfect. At small scales, galaxy physics takes over. At large scales, the cosmic horizon limits structure. But over intermediate scales, it's surprisingly pronounced. The mathematical beauty of cosmic voids suggests something deep. The universe's structure isn't arbitrary or accidental. It follows from comprehensible physical laws that generate predictable patterns. The voids, despite their emptiness, participate in this lawful structure. They're mathematical objects as much as physical ones, describable through equations and predictable from theory. Void galaxies, evolutionary laboratories. Let's return to void galaxies with deeper focus, because these objects represent one of astronomy's most valuable natural experiments. Galaxy evolution is complicated. Galaxies interact with their environments in countless ways. They merge with neighbors, they ram through intergalactic gas, they're tidally stripped by massive neighbors, they're subjected to galactic winds from nearby supernovae and active galactic nuclei. Disentangling internal evolution, what galaxies do on their own, from environmental effects, what happens because of where they live, is extraordinarily difficult. Void galaxies solve this problem by eliminating environmental effects almost entirely. They evolve in isolation, far from any significant neighbors, unaffected by the processes that shape galaxies in denser environments. They're control samples showing what galaxy evolution looks like when it's purely internal. And what astronomers find is remarkable. Void galaxies are systematically different from galaxies in typical or dense environments. They're overwhelmingly late-type spirals or irregular galaxies. While elliptical galaxies dominate in galaxy clusters, they're rare in voids. This tells us that elliptical galaxies form primarily through environmental processes, mergers and interactions that occur in denser regions. They're actively forming stars. While many cluster galaxies are red and dead, no longer forming stars, their stellar populations aging and reddening. Void galaxies maintain vigorous star formation. This reveals that star formation quenching in dense environments is environmentally driven, not an inevitable consequence of galaxy aging. They're gas-rich. Cluster galaxies often have their gas stripped away by ram pressure as they plow through hot intra-cluster gas. Void galaxies retain their gas, which fuels continued star formation. The gas itself tells us about chemical evolution. Void galaxies tend to have lower metallicity, fewer elements heavier than hydrogen and helium, because they've recycled less material through multiple generations of stars. They're smaller on average. Without mergers to drive growth, void galaxies remain modest in size. This demonstrates that galaxy growth isn't just about gas accretion and star formation, but depends critically on hierarchical merging, smaller galaxies combining to form larger ones. They show rotation patterns consistent with undisturbed evolution. Many cluster galaxies have kinematic peculiarities, rotation axes that don't align with their structural axes, counter-rotating cores, other signatures of past interactions. Void galaxies typically show clean, regular rotation, suggesting their history has been mercifully simple. All of this has profound implications for galaxy formation theory. It allows astronomers to isolate which aspects of galaxy evolution are intrinsic, would happen regardless of environment, and which are environmental, depend on where the galaxy lives. But void galaxies also raise questions. How did they form in the first place? Standard theories suggest galaxies form in dark matter halos, gravitationally bound clumps of dark matter within which normal matter can condense. But dark matter halos should be rare in voids, since dark matter is itself underdense there. So where did void galaxy halos come from? The answer seems to involve timing and cosmological initial conditions. Even in regions destined to become voids, there were tiny overdensities, places where matter was marginally more concentrated. These overdensities could collapse early in cosmic history, before the void fully evacuated, forming dark matter halos and subsequently galaxies. These galaxies then watched as their neighborhood emptied around them. They formed in place and remained there, preserved fossils of an earlier era when matter distribution was less extreme. They're survivors, in a sense, galaxies that managed to condense before it was too late, before matter drained away entirely. This makes void galaxies valuable for another reason. They constrain theories of structure formation. Their existence, properties, and distribution must be explained by any successful cosmological model. If a theory predicts too few void galaxies, or galaxies with the wrong properties, it's incomplete or incorrect. Currently, simulations do reasonably well at producing void galaxy populations matching observations, though some discrepancies remain. These remaining puzzles drive ongoing research, pushing theorists to refine their models and observers to obtain better data. If you're fascinated by how these isolated island universes are teaching us about galaxy evolution, please consider liking this video and sharing it with others interested in astronomy's detective stories. And I'm genuinely curious, do void galaxies seem tragic to you, isolated and alone, or fortunate, free from the violent interactions that disrupt galaxies in denser environments? Share your perspective in the comments. The anthropic void, selection effects, and observation. Here's a subtle but important question. Could the existence of observers like us depend on cosmic structure in ways that influence what we observe? This is an anthropic argument, and it requires careful handling. The anthropic principle, in its weak form, simply states that any observations we make must be compatible with our existence as observers. We necessarily find ourselves in a universe and location compatible with our arising. Applied to cosmic voids, this suggests something interesting. Complex life, presumably, requires planets, which require stars, which require galaxies, which require regions where matter has concentrated. Observers like us probably cannot arise in void interiors, where galaxies are scarce and matter sparse. This means observers will necessarily find themselves in atypical cosmic locations, in galaxies, which cluster in filaments and walls, not in voids. Most of the universe by volume is void, but most observers, if they exist elsewhere, likely inhabit non-void regions. Does this matter for cosmology? Perhaps. It means that any observations we make come from a biased location. We're not sampling the universe randomly. We're sampling it from a location selected specifically because it can support observers. This could skew our perspective in subtle ways. For instance, the cosmic web structure is more apparent from our location than it would be from a void interior. We can easily observe many galaxies, see their clustering patterns, and infer large-scale structure. Void-based observers would have a much harder time discovering the cosmic web's full complexity. More subtly, certain cosmological measurements might be systematically biased if taken from typical galaxy locations rather than from locations distributed randomly through space. For example, the local cosmic expansion rate, the Hubble constant, might vary slightly between high-density and low-density regions. If observers exist only in high-density regions, their measurements of cosmic expansion might not perfectly represent the universe's average. Cosmologists are aware of these potential biases and work to account for them. Statistical techniques and careful modeling can compensate for observational selection effects. But the deeper question remains: are there aspects of cosmic structure that we're systematically failing to observe because of where we're located? The anthropic principle also intersects with void studies in another way: fine-tuning. The universe's fundamental constants, things like the strength of gravity, the mass of elementary particles, the energy density of dark energy, appear finely tuned to allow structure formation. Change them significantly, and cosmic structure as we know it wouldn't exist. Voids are part of this story. The contrast between voids and filaments depends on precise balances between cosmic expansion, gravitational attraction, and dark energy's repulsion. If these forces were balanced differently, the cosmic web might look completely different. Perhaps no voids at all, or perhaps nothing but voids with no structure. The fact that cosmic structure exists in a form compatible with galaxy formation and presumably with life raises questions. Is this fine-tuning coincidental, or does it require explanation? Some physicists argue for multiverse theories, many universes with different constants, and we necessarily observe one compatible with our existence. Others seek different explanations. Voids don't resolve these debates, but they're part of the cosmic structure that requires explanation. The universe's organization into regions of presence and regions of absence, with properties that allow both to coexist and evolve, is part of the overall pattern that any complete cosmological theory must account for. The texture of nothing, quantum fields and voids. Even in the emptiest voids, something interesting happens at the quantum level. This is where physics becomes delightfully strange. Quantum field theory tells us that what we call empty space, vacuum, isn't truly empty. It's filled with quantum fields, and these fields fluctuate constantly. Virtual particle-antiparticle pairs pop into existence and annihilate almost instantly. Quantum uncertainty ensures that even in perfect vacuum, there's always activity at the smallest scales. In cosmic voids, we have regions approaching this quantum vacuum state. The matter density is extraordinarily low, perhaps 1 atom per 10 cubic meters, compared to trillions of atoms per cubic centimeter in ordinary matter. Between these rare atoms lies space that's as empty as space can physically be. But that space isn't inactive. Quantum fields still fluctuate. Dark energy, which might be the energy density of vacuum itself, pervades even the emptiest voids. The electromagnetic field exists everywhere, even where no photons are traveling. The Higgs field, which gives particles mass, maintains its non-zero vacuum expectation value throughout every void. This raises fascinating questions. Is the vacuum in voids identical to the vacuum elsewhere, or could there be subtle regional variations? Could quantum field properties differ slightly between voids and dense regions? Current theory suggests the vacuum state is uniform, but it's worth verifying experimentally. Some speculative theories predict vacuum phase transitions, spontaneous changes in quantum field configurations that could propagate through space. If such transitions occur, voids might be affected differently than dense regions. An expanding bubble of altered vacuum state might propagate faster through voids where matter offers no resistance. More concretely, cosmic voids might offer ideal locations for detecting extremely subtle phenomena. Without dense matter and its associated electromagnetic noise, without strong gravitational fields, voids are quiet in ways that dense regions aren't. If we could somehow position a detector in a void, purely hypothetically, given the distances involved, it might detect faint signals overwhelmed by noise elsewhere. This connects to searches for things like dark matter direct detection or gravitational waves from the early universe. These searches require extraordinary sensitivity and benefit from low-noise environments. While we can't actually place detectors in cosmic voids, understanding the void environment helps theorists predict what such measurements might reveal. There's also the question of whether quantum fluctuations in the early universe might have affected void formation. The density fluctuations that seeded cosmic structure originated as quantum fluctuations during cosmic inflation, the exponentially rapid expansion in the universe's first instance. Those primordial quantum fluctuations were stretched to cosmic scales and eventually became the variations that evolved into the cosmic web. Did the initial fluctuations contain information that specifically determined where voids would form? Was the distribution of voids predetermined by quantum physics in the universe's first moments? The answer appears to be yes. The statistical properties of cosmic structure, including voids, trace back to quantum phenomena during inflation. This creates a profound connection. The largest empty structures in the universe have their origins in the smallest scale physics we know. Quantum uncertainty, operating at scales billions of times smaller than an atom during the universe's first fraction of a second, determined where billion light-year voids would eventually form. The quantum and the cosmic are intimately connected. Cultural and historical perspectives on emptiness. Before we had telescopes powerful enough to discover cosmic voids, human cultures were already contemplating emptiness, absence, and void as philosophical and spiritual concepts. It's worth briefly considering how these ancient perspectives resonate with modern cosmological discoveries. In Eastern philosophy, particularly Buddhism and Taoism, emptiness, sunyata in Sanskrit, wu in Chinese, is a central concept. But emptiness in these traditions doesn't mean mere absence. It refers to a pregnant nothingness, a potential from which things arise and to which they return. The void is generative, not barren. This resonates intriguingly with cosmic voids. They're not absolute emptiness, but regions of reduced density that play active roles in cosmic structure. They expand, they evolve, they influence surrounding matter. They're defined by relationship rather than absolute absence. They're empty compared to their surroundings, not empty in any absolute sense. The Taoist concept of wu wei, effortless action, or action through non-action, suggests that sometimes the most powerful influences are the subtlest, the most apparently passive. Cosmic voids, in their passive expansion, shape the cosmic web as surely as gravity's active attraction shapes galaxy clusters. They influence through absence, act through emptiness. In Western philosophy, the concept of void has different connotations. Ancient Greek atomists like Democritus proposed that reality consists of atoms moving through void, infinite empty space that allows motion and change. Without void, atoms would have no room to move. Reality would be a static plenum. This insight remains relevant. Cosmic structure requires emptiness. Without voids, Matter would be uniformly distributed, and there would be no structure, no galaxies, no stars, no life. The voids enable the cosmic web's existence. They're not just gaps in the pattern, but essential components of it. Medieval and Renaissance philosophers debated whether true vacuum could exist, or whether nature abhors a vacuum, as Aristotle claimed. The development of vacuum pumps and experimental physics eventually proved that vacuum can exist and has measurable properties. Space itself could be evacuated. Absence could be created and studied. Cosmic voids represent nature's own vacuum experiments, conducted at scales that dwarf anything achievable in laboratories. They're natural test cases showing what happens when matter is evacuated from vast regions, leaving something approaching true vacuum. In art and literature, void and emptiness often evoke existential themes: meaninglessness, isolation, the terror of insignificance. The cosmic void has become a metaphor for existential dread, the fear of nothingness. But there's another artistic tradition that finds beauty in emptiness. Japanese aesthetics like Ma, negative space, and wabi-sabi, beauty in imperfection and impermanence. These traditions recognize that emptiness frames presence, that absence gives meaning to existence, that simplicity can be more powerful than complexity. This aesthetic resonates with cosmic voids. They frame the cosmic web, making its structure visible and comprehensible. They provide contrast that makes galaxies and filaments significant. The universe's beauty depends on having both filled and empty regions. Pure presence would be as meaningless as pure absence. Modern artists have been inspired by cosmic voids. They've created installations exploring themes of scale, absence, and structure. They've used voids as metaphors for psychological space, for the gaps in understanding, for the vast territories of ignorance surrounding islands of knowledge. These cultural and artistic engagements with void concepts remind us that cosmic voids aren't just scientific objects. They're phenomena that connect to deep human concerns about existence, meaning, and our place in reality. The science of cosmic voids is richer for considering these broader contexts. The information content of emptiness. Here's a question that sounds paradoxical. How much information does a cosmic void contain? Information theory provides frameworks for quantifying information content. Typically, information is associated with structure, pattern, complexity. A complex message contains more information than a simple one. A detailed image contains more information than a blank canvas. By this logic, cosmic voids should contain minimal information. They're as close to featureless as cosmic structures get. Their primary characteristic is lack of galaxies, lack of matter, lack of structure. But this is too simple. Cosmic voids actually contain substantial information encoded in subtle ways. First, their existence conveys information. Knowing that a void occupies a particular region of space tells you something about cosmic history. This region started slightly underdense and has emptied over time. The void's presence is informative about initial conditions and cosmic evolution. Second, void properties encode information. Size, shape, degree of emptiness, expansion rate. These parameters carry information about cosmological processes. Different cosmological models predict different void property distributions, so measuring voids provides data that constrains theories. Third, voids contain information about their boundaries. Where does the void end? How sharp is the transition to surrounding structure? These boundary properties reveal how voids interact with the cosmic web. Fourth, even void interiors aren't information-free. The few galaxies within voids have particular properties and distributions. The diffuse gas has specific density and temperature profiles. These features encode information about void formation and evolution. From an information-theoretic perspective, voids are lower information than filaments or galaxy clusters, but they're not zero information. They're part of the cosmic information landscape, regions where information density is low, but not absent. This connects to deep questions in physics about the relationship between information and physical reality. Some theories suggest that information is fundamental, that physical states are ultimately information states, that matter and energy are ways of encoding information about the universe's configuration. From this perspective, cosmic voids are low information density regions in a universe-wide information field. They're sparse data in the cosmic dataset. But they're still data, still part of the total information content that defines our universe. There's even a provocative connection to holographic principles in quantum gravity. Some theories suggest that a region's information content is proportional to its surface area, not its volume. That three-dimensional space somehow encodes information on two-dimensional boundaries. If true, cosmic voids' information content would be determined primarily by their surfaces, their boundaries with surrounding structure, rather than their interiors. This would be poetic. Voids defined by their edges rather than their centers, characterized by their relationship to surrounding fullness rather than their internal emptiness. It would make voids fundamentally relational, existing only in contrast to what surrounds them, defined by boundaries rather than contents. Whether this holographic perspective applies to cosmic voids remains speculative, but it suggests that even empty space might harbor mysteries we're only beginning to appreciate. Existential reflections, living with voids. As we near the end of this extended exploration, let's return to the human dimension. What does it mean, existentially and emotionally, that cosmic voids exist? There's something unsettling about voids. They challenge our intuitive sense that the universe should be filled, that existence should predominate over absence. We're creatures who inhabit a matter-rich environment, a planet with solid ground, surrounded by atmosphere, orbited by a star, part of a galaxy containing billions of stars. From this perspective, the universe seems abundant, full, rich with structure. But voids remind us this is a parochial view. Most of the universe is empty. The matter-rich regions we inhabit are anomalies, rare exceptions to a general rule of emptiness. We live in one of the universe's interesting neighborhoods, but most cosmic real estate is profoundly boring. Just empty space stretching for hundreds of millions of light years. This realization can trigger a kind of cosmic loneliness. If most of the universe is empty, if separation and isolation are more common than connection and clustering, what does that say about existence? Are we, all conscious beings anywhere in the universe, just rare accidents in an overwhelmingly empty cosmos? But there's another way to view it. The voids make our existence more remarkable, not less. Precisely because most of the universe is empty, the regions where matter has concentrated and structure has formed are special. We inhabit an improbable corner of reality, a place where the typical emptiness has been overcome, where complexity has emerged against the general tendency toward simplicity. The voids also offer a kind of perspective. When you contemplate scales of hundreds of millions of light years, human concerns, personal anxieties, social conflicts, even planetary crises can seem cosmically insignificant. Not that they don't matter, but they matter in a different register, against a background of such vast emptiness that our local dramas are infinitesimally small. Some find this perspective liberating. If the universe is mostly empty void, if human existence occupies a negligible fraction of space and time, perhaps we can let go of certain burdens, certain self-imposed importance. Cosmic perspective can breed humility and peace. Others find it troubling. If we're so cosmically insignificant, does anything we do matter? If the universe is vast and mostly empty, indifferent to our existence, where do we find meaning? These are ancient philosophical questions, but cosmic voids give them visceral force. They're not just thought experiments, but real territories, actually existing empty regions that dwarf human comprehension. Perhaps the resolution is this: meaning is local, not cosmic. The universe as a whole may be indifferent. Voids don't care about human existence. But meaning emerges from relationships, consciousness, care. We create significance through attention and intention, not by discovering it written into cosmic structure. From this view, voids are simply features of physical reality, neither meaningful nor meaningless in themselves. They become meaningful only when conscious beings contemplate them, study them, wonder about them. The meaning is in the contemplation, not in the voids. And perhaps that's enough. Perhaps it's even beautiful that consciousness can arise in small pockets of structure scattered through vast emptiness, and that this consciousness can turn its attention outward, recognize the emptiness, measure it, understand it, and find in that understanding a kind of meaning that the emptiness itself doesn't possess. We are the universe looking at itself, as Carl Sagan famously said. And sometimes, when we look, we see mostly emptiness. But we see it, we understand it, and in understanding, we create meaning where none existed before. Closing reflections. The gift of cosmic voids. As this extended journey through cosmic emptiness comes to its conclusion, what have we learned? We've learned that the universe is organized on scales almost impossible to comprehend, with structures of presence and absence that dwarf anything in human experience. We've learned that emptiness isn't merely the absence of things, but is itself a feature, a phenomenon, something that can be studied and understood. We've learned that cosmic voids tell us about the universe's history. They're regions where matter has been evacuated over billions of years, territories that preserve information about cosmic evolution. They constrain our theories of dark matter and dark energy, those mysterious components that dominate the universe's budget yet remain poorly understood. We've learned that voids affect nearby structures, that they expand and evolve, that they're dynamic rather than static. They're not gaps in the cosmic web, but integral parts of its architecture, as necessary as the filaments and clusters that surround them. We've learned that even the emptiest voids aren't truly empty. They contain rare galaxies, diffuse gas, dark matter, dark energy, and quantum fields. They're as close to nothing as cosmic regions can be, yet they're still something, still part of the physical universe, still worthy of study and wonder. And perhaps most importantly, we've learned that cosmic voids invite contemplation. They prompt questions about existence and absence, significance and insignificance, the rare and the common. They challenge us to expand our perspective, to recognize that the universe is stranger, larger, and more varied than our local experience suggests. The loneliest places in the universe aren't just scientific objects. They're prompts for wonder, invitations to think differently, opportunities to recognize both our cosmic insignificance and our unique capacity for understanding. Thank you for journeying through this exploration of cosmic emptiness. If these reflections have moved you, please share this video with others who might appreciate this contemplative approach to astronomical wonder. And I genuinely value your thoughts. How do cosmic voids make you feel? What questions do they raise for you? What meanings do you find in contemplating such profound emptiness? The comment section is open for your reflections, and I read and consider every thoughtful response. This exploration was enriched by your attention, and I'm grateful you chose to spend this time contemplating the universe's loneliest territories with me. Until next time, keep looking up, toward the stars, and beyond them, toward the great dark spaces that frame and define the cosmos.